Hi Chemistry 12-2 and welcome to video 3 for week 6. So we're still talking about acids and bases. Our video 1 this week was on Arrhenius acid and base definitions. Our second video was on Bronsted-Lowry acid and base definitions and pH indicators. And our third video today is going to be on predicting acid-base reactions. So it's one of the outcomes in our curriculum, but unfortunately it's not covered in our textbook. So the information I'm going to talk about today, I've pulled from the Nelson textbook, section 15.2. So pay close attention because you will not be able to check this out in your textbook. So we're going to talk about predicting acid-base reactions, and we often refer to it as the 5-step method. And that's because there's 5 steps we're going to cover as we go through this. So I'm just going to quickly go over the steps and then jump right in and look at a couple examples. The first step, it says list all entities present in water environment. So we'll talk about that. Second step, identify all possible acid and bases using Bronsted-Lowry definitions. We can use our acid-base table to help us do that. Number 3, identify the strong acid and the strong base. So that's what SA stands for. Identify the strongest acid of the group and the strongest base present in the beaker. Again, we'll use the acid-base table to do that. In step 4, transfer 1 proton from the acid to the base and predict the conjugate base and the conjugate acid as products. So here we're going to use Bronsted-Lowry definitions, and our acid's going to donate at H to the base. And remember, the word conjugate means partner, and therefore the conjugate base will be what the acid looks like after it donates the H, and the conjugate acid will be what the base looks like after it accepts the H. And our last step here is predicting equilibrium. We have a generalized rule that we'll follow. We really can only predict if it's greater than 50% or less than 50%. So our goal really is to see if the products are favored or if the reactants are favored. Now this seems kind of off because these guys are on different levels, but they're on different levels for a reason. There's a generalization that says if your strong acid is higher on the acid-base table, and your strong base is lower on the acid-base table, then you're always going to have a greater than 50%. So we'll come back and talk about that generalization in a bit. 2 things to remember when we talk about these steps. The first one is all metal ions are assumed to be spectator ions. So metal, right? Metal's on the left side of the table. If you have an ion that's a metal ion, chances are it's not going to be involved in the reaction. It'll be in the beaker, but it won't be involved in the acid-base reaction. And for this course, quantitative reactions cannot be predicted. So we can't decide if it's 99% yield. All we can do is indicate if it's greater than or less than 50%. If you have a quantitative reaction, it'll be indicated for you. So step 1 is what I want to start with, because we need to review how to list entities present in water environment. You may have talked about this in grade 11, you may not have. So I thought we'd probably just assume you haven't, and we can take a look at this table. So this table here, we're going to take a few minutes to look at. I posted it in files. It's in the week 6 reference material, and it's a pretty important table to have. There's a lot of information here, and some people try to memorize it, but I think it's actually better if you listen in the next few minutes, and we'll talk about each of these entities and rules, and I think the more you use the rules, the more you'll remember them. Okay, so when you take a look at compounds, generally speaking, there's 4 categories that compounds can fall into. Ionic compounds, molecular compounds, acids, and bases. So those are 4 basic basic categories that compounds can fall into. So we're going to use those categories, and we're going to talk now. Entities is really just a fancy way of saying, will the compound split up into its ions, or will the compound stay together as a unit? That's really what they're asking for when they ask for the major entities present in a water solution. So if we take a compound and dump it into a beaker of water, will the compound break up into its ions, or will the compound stay together as a unit? Okay, that's what we're trying to decide. So if we take a look at our first category, it's an ionic compound. And ionic compounds, if you recall, because some of us are weak at identifying what category they should be put into, but if you recall, ionic compounds always start with a metal, so that's the best way to identify them. And ionic compounds, the rule we've got to look at is we want to know, do they split up into their ions or not? It all comes down to solubility in water. And we have a table on the back of our periodic table. So if you're okay with using that solubility table, great. If you're weak on that and you need a little bit of help, please email me or even bring it up on Tuesday or Thursday. We can take a quick look and talk about the solubility table, because that's really important here. With ionic compounds, it's all about, are they soluble or not? If ionic compounds are soluble, like sodium chloride, they split up. So the entities present would not be sodium chloride as a unit, but it would be two separate entities. You'd have your Na positives and your Cl negatives. So entities are really counting to see if ions are present or if the compound stays as a unit. So NaCl breaks apart into its two ions. Now we've dumped it into liquid water, so the entity water, H2O liquid, it's always going to be there because it's kind of our base, and we're putting these ions or these compounds into water. So you can bank on H2O liquid being an entity all the time. If you have low solubility, it's still an ionic compound, but it has low solubility, for example, calcium carbonate, you'll notice it stays as a unit. So low solubility means stay as a unit. It's still an entity, but it's an entity as an individual unit. Here, there's two entities, two ions, Na and Cl negative. Here, one entity, CaCl. So with ionic compounds, it's all about their solubility. Bases, you really don't even need a fourth compound, or rather a fourth category, because all bases are ionic. So these guys could actually be lumped together, and they have exactly the same rule. If you're looking for a base, look for that OH negative, remember. And the rule is the same with bases. If it has high solubility, and check your chart, okay, you can find out for any base if it has high solubility or not. If it has high solubility, look at that. It splits apart. It breaks up into individual ions. Remember, ions have a charge and they're AQ, right? If it has low solubility, like calcium hydroxide, it stays together as a unit. So low solubility, staying together as a unit. High solubility, breaking apart into its ions. Notice H2O liquid, always an entity. If you go into the next category, it's molecular substances. And if you recall, molecular substances start with a nonmetal. Okay, so look for that nonmetal. Again, you can look at the solubility, but really, it's a nice general rule for molecular compounds. The general rule is they never break up into ions because they don't have ions. Molecular compounds, remember, they're a group of atoms sharing elements, or sharing electrons rather. So there's no ions involved. So how could they split up into ions if there's no ions involved? So regardless if they have high or low solubility, sugar has high solubility, octane, which we find in gasoline, has low solubility, but both of them stay as a unit. They don't break up into individual ions, okay? One difference you can note, if it has high solubility, it turns into aqueous, so the state changes. Here it's solid. When we put it in water, because it has high solubility, it gets a state of aqueous. Here, octane, it has low solubility. When we put it in water, it contains, or it remains as a liquid. But for our purposes, the key that's important here is molecules never break apart. Molecules always stay as a unit, okay? And our last category are acids. And from last week, we know that acids can be strong acids and acids can be weak acids. With strong acids, we've got our acid table here, right here, acid-base table. Remember, the 6 acids at the top are your strong acids. Everything else below that are weak acids. And so in our table, you can look at the solubility if you want, but strong acids, they have 100% ionizing. They love to break up into their ions, so they do. So strong acids will break apart into individual ions. Weak acids do not. They might be partially, but they're just so poor at ionizing, they prefer to stay together as a unit. And so strong acids break apart, weak acids do not. So there's your 4 categories: ionic compounds, molecular compounds, acids, and bases. Bases really acting like ionic compounds. If you look at elements, our other category, elements, you can't break them up like compounds. Elements can be split, but they're not going to be split into ions. So they always have elements have low solubility, but they're always going to remain exactly the same when they are written as an entity as opposed to just as an element. Okay? But take note, H2O liquid all the way through, always an entity, H2O liquid. Okay, I think we're ready. So if you take a look at this example, it says, suppose some spilled oven cleaner containing aqueous sodium hydroxide is neutralized with vinegar. Predict the predominant acid-base reaction. So we're going to use our 5 steps here. We're going to predict what acid-base reaction would occur. The first thing we need to look at are, and you'll notice they haven't given us any chemical formulas. And some of you guys are weak with that. So here's a place to practice. Aqueous sodium hydroxide. Do you know how to put that into a chemical formula? Sodium hydroxide. It's aqueous, so I put AQ there. Our other player is vinegar. And vinegar you might not know because that's a traditional name. And so you might have to look that one up, but some of you guys would remember that it's acetate or hydrogen acetate or acetic acid or ethanoic acid. There's lots of ways of saying it, but that's going to be our acid. And it's an aqueous sodium hydroxide, so we know that this has been dumped into a beaker of H2O water. So these are the compounds that we have here, okay? Now we're ready to start. We have to get them into their chemical formulas before we can start. If we recall, and now I'll go back to our steps, our first step here, it's list all entities present in water environment. So if we come back here, we have to look at each of our compounds and see if they split up. That's what they mean by listing entities. So if you look here, what category does it fall into? It starts with a metal. It's going to be an ionic compound. So you have to check to see if it has high solubility or low solubility. That's the rule, right? Ionic compound, check. High or low solubility, high solubility it splits apart, low solubility it doesn't. You can also recognize it as a base, okay? It's got the OH, so it's also a base. Same rule, high solubility or low solubility. I highlighted Na because Na is from group 1. And if you look at your solubility chart, everything in group 1 is soluble. So what's going to happen here is we're going to have a split. So our entities are going to be Na positive and OH negative, okay? And just for time-wise, I'm not going to change that aqueous into a subscript or into a subscript. I'm going to just worry about my charges. You guys will know that you could change that into a subscript if need be, okay? So we actually get 2 entities out of this compound. It breaks up into its ions, so we get both of those entities, okay? And just to be, in touch with our grammar, we can put a comma between that. Then we move on to the next compound, okay? We recognize it as, hopefully you recognize it as an acid. Acids start with an H or end with COOH. And so we've got to decide what's the rule with acids. So you'll come back and forth to this chart quite a bit when you start. You'll be surprised how quickly you remember them. But acids down here, the rule is we don't really care about solubility. It's all about if it's strong or weak. And if you recall, on our acid-base table, there's only 6 strong ones, and those are the top 6 right here. The rest are weak. So it falls into our weak category. So weak acids, they don't like to split up. They like to stay together. So I'm just going to clone this guy and bring him down here. Okay? And I'll clone this guy and bring him over. And so we're one step closer. We also have water. Water's always an entity, so we need to decide water never splits up. And you might wonder why. Some people just always include it, but the reason why we can always include it is because water is a molecule. And if you remember the rule for molecules, I know you're yelling it at me right now. If you remember your rule for water molecules, you will notice, I'm just trying to find it here, it's a molecule, high or low, doesn't matter. They always stay together as their unit. So molecular compounds aren't made up of ions. They can't split into ions. So now we have all of our entities. Our first guy split up. He was an ionic compound or a base that had high solubility. Our second guy was a weak acid, did not split up. Our third guy was a molecule, did not split up. Our next job is to, if we go to our steps, so we've done our first one, list all entities present in the water molecule, water environment. This takes a little bit of time now, but as you practice, you'll get better at it. Number 2, identify all the possible acids and bases in the reaction. So now what we have to do is use this baby again, and if you haven't, you might want to pause and find that acid-base table and come on back. This acid-base table is important because it's going to allow us, you notice there's one column that says acids and one column that says bases. Don't worry about the conjugate. So if you're wondering if something's an acid, look to see if it's in this column. If you're wondering if something's a base, look to see if it's in this column. You might find something that occurs in both columns, and that's okay. Remember the term amphoteric. Some compounds work as an acid and a base. So if we go back to our compounds or our substances, search for Na positive. And if I was mean, I'd let you search forever and ever and ever. But what you're going to find out is it doesn't occur in either of the columns because it is that metal ion we were talking about earlier. So sodium is a metal ion, and metal ions are spectator ions. They don't take part in the reaction. They're there in the beaker, but they don't take part in the reaction. So we can get rid of that sodium right away. Then we move on to OH, and we go to our table, and we search for OH. We search on both sides, and again, once you get better acquainted with this table, you'll not have to search as much. And you'll see OH is down here, -1. And so it's on the base side. So we come back, and it gets a B. And I tend to put my B's on the bottom, that's just me, and my A's on the top. So this is going to be a B. If I look here, you guys know, you switch back, you find it, it's on the acid side. And again, you get a little better at it as you practice this. So this is going to be an A for acid. So I'm just using my acid-base table. I'm checking to see what column each of these belong to. And eventually we get to water. And when we get to water, what happens is you'll find it's in the acid column, but you also find it's in the base column, okay? And that shouldn't be a surprise because we said that it was amphoteric, so it can act as an acid and it can act as a base, right? So you can find it right at the bottom on the acid side and close to the top on the base side, okay? And boom, we're done. We've labeled our acids, we've labeled our bases. This guy is both. So we've done step 1 and we've done step 2. Step 3, identify the strong acid and the strong base, Sa and Sb. So if you come back here, you'll see 2 things have been labeled as base and 2 things have been labeled as acid. So we now have to take the time to decide which one of our 2 bases is stronger and which one of our 2 acids is stronger. Let's start with bases. So here we have OH negative and we have water. So how you determine, again, is that acid table. The acid table, if you don't have one, you can't do this 5-step method. You need your acid-base table. I just want to remind you, here's your strongest acids, and the acids decrease in strength as you go down. The bases, if you recall, are opposite. Your strongest bases are down here, and they decrease in strength as you go up. If you recall, the weaker the acid, the stronger the conjugate base, or vice versa. The weaker the conjugate base, the stronger the acid, okay? So acid decreases in strength on the way down, bases decrease in strength on the way up. So that can be confusing, so be careful with that. This is to help you out. Acids are stronger when they're at the top, bases are stronger when they're at the bottom. So when we look at OH negative and H2O on our base side, we find our H2O up here, and we find our OH negative down here. So OH negative is the strongest of the bases. And so we let people know that by putting a big S in front of it. So OH negative is going to be our strongest base. We do the same thing for acids, but just be careful with the direction. So with acids, when you look at it, our water is down here at the bottom, and our acetic acid is here in the middle. So acetic acid is higher, it's stronger, and so we put a big S in front of acetic acid. Alrighty, so Whew, step 1, step 2, step 3. Acid-base table, very, very important. So now what we're going to do is our step 4. So the step 4 is finally we're getting into a reaction. Transfer 1 proton from the strong acid to the strong base. So that's why we wanted to label our acid and base, because those are going to be the two that are going to be involved in the reaction. We haven't done a reaction yet. We've just filtered our information. So what we're going to do is we're going to clone this baby, and we're going to bring the strong acid down here. So that's the one we're going to work with now. That's why we identified the strong base. That's why we identified the strong base. We're also going to clone this guy, and we're going to bring in our strong acid, okay? And our strong acid right down here. I guess we can just bring the whole thing down if we want, okay? Well, maybe we shouldn't. Maybe we should leave it as is. Just so if you look back at this, you'll see how it was actually done. So we'll just clone that instead. I don't know where that went now. Clone it. Clone it. Bring our base down here. So we've got our base. It is strong. We've got our acid. It is strong, and that's why we wanted to identify those, because those are the two that are going to be involved in our reaction. So we're going to react these guys together, okay? Now, we can't just have reactants, we have to have products, but we're okay with that because we know how these acids and base work. It is going to be equilibrium, so bring in your equilibrium arrows, okay? And if you recall that ionizing H, and we worked a lot with this last week, our ionizing H is the one that's going to be donated. So this guy is going to be donated to the base. And when it's donated to the base, and I'll write it this way, I want to put liquid here. We get water, okay? And that's what this guy looks like. Now let's look at the charge. This guy was -1. He's gaining an H. When you gain H's, you get more positive. So he becomes neutral. And we get this poor little fella without his H, right? And so clone him, bring him over here, drop his H. Now what's going to happen? He's lost an H. He was neutral. He's lost an H. When you lose H's, you get more negative. So we've got, this is the conversation you have to have with yourself when you're working with ions, okay? And squeeze this in here a little bit. You get the idea. We have our reaction. We have one more step to go. So here we have our CH3COH. We have our OH negative. They've exchanged an H. We have water, and we have H2O. And what we're going to do is we're going to now do our fifth step. And our fifth step is figure out, and a lot of people forget this fifth step. They're so excited to get their equation, they stop there. But don't forget the fifth step. You need to figure out, is it greater than 50% or less than 50%? I'm going to explain this little generalization rule for you. And what I'm going to do, because people for some reason have a really tough time with this. So Mrs. Tate has come up with this idea, and I think it's ingenious, so I'm going to use it. And so how do you tell, once you've got your reaction, how do you tell if it's greater than or less than 50%? Because you can't forget that last step. We want to know, are the products favored or the reactants favored? And we, once again, surprise, surprise, we go to our acid-base table. So what you're going to do, it seems silly, but you're going to use your left hand, and that's going to represent your strong acid, and you're going to represent your strong base with your right hand. So left hand, strong acid, right hand, strong base. And what you're going to do is you're physically going to put your finger, your left index finger, on acetic acid, because that was our strong acid, and you're going to put your right index finger on OH negative, and that's way down here. So your OH negative is down here, and your acetic acid is up here. So you've got your left hand index finger on acetic acid, you've got your right index finger on OH negative physically. What you need to do now is this is what the rule is. If your left hand finger is higher than your right hand, if the strong acid is higher on the table than the strong base, then you have a greater than 50% reaction. If vice versa, if your left hand is higher than your right hand, you're going to have a less than 50%. So what I mean by that, it's hard when you're just saying it, but I think if you see it, it'll help. So acetic acid was up here, and OH negative was down here. So our left hand was higher on our table than our right hand. That's always going to mean greater than 50%. Okay? So in this case, our reaction is going to favor the products. It's greater than 50%. If, for some cases, the right hand is higher than the left hand, then what's going to happen is it's flip-flop. You get a less than 50%. So you just have to remember, left hand high, greater than 50%, which is in this case. Or left hand low, right hand high, it's going to be less than 50%. Okay, I hope that helps, because a lot of people have a hard time with that last step, deciding if it's greater than or less than 50%. With us, our left hand is higher, so we have greater than 50%. And that finishes off our reaction, because now we know that we're favoring the products. Okay? Whew, 5 steps. A long explanation, but hopefully that helps. And I'm going to do one quick one. I know we're at 26, but I'm going to do one more quick one with you, just to make sure you can work through the steps and you know how to use that generalization, how to use the greater than or less than 50%, how to tell. Okay, next question. We have ammonia, nitric acid, and we have, it says ammonium nitrate fertilizers produced by the quantitative reaction of aqueous ammonia with nitric acid. Write a balanced acid-base equilibrium equation. So I'm going to use the same steps as I used before, and we are making, so we have to be careful of that, we're making ammonium nitrate. How are we making it? We're using aqueous ammonia, and we are using nitric or nitric acid. Okay? Boom. Again, not our favorite, but we have to be confident in writing out chemical equations for chemical formulas for these things. So this is your ammonium nitrate. So ammonium is NH4 and nitrate is NO3, and ammonium is +1 and nitrate is -1. So we just need 2 of them, one each I should say. We also have ammonia, not to be confusing, and ammonia, it says aqueous. Okay, so we'll put an aqueous there, and we'll bring that down as a subscript. So we have some ammonia here, and we have some nitric acid and or nitric acid. So HNO3, and that's an acid. Okay, so important to get what you need right off the bat, and if you mess this up, it can mess everything else up. So you got to be careful, double check maybe once you're done to see if you've got these correctly. Okay, and what's the one other thing we always have to include, because it's in an aqueous solution? And if you're screaming at me and saying, water, Miss Ryan, you're absolutely right. Okay, so that's always another player. Don't forget it. Sometimes it's really important because it ends up being your strong acid or your strong base. So you've got to remember to always include the water when you're doing that. Okay, so this is what we've got. Now we've got to be careful here though, because the ammonium nitrate is produced. It's not here at the beginning. Okay, it's what we're making. So we're going to ignore it for now, because when we start, these are the things that are in our beaker. Okay, so let's kind of set this to the side, and we'll talk about that a little later. So if we go to our steps, and I'm going to try and get through this quickly because I know I'm running out of time. If we go to our steps, here we see we need to list our entities, identify our acids and bases, and figure out which one's strong and which one's weak. So if we look at our entities, we go down and we've got NH3. NH3, it's not ionic, doesn't start with a metal. It's not an acid, not a base. It's molecular, okay? It's molecular, starts with a non-metal. And what's the rule for molecular? Molecular compounds, they do not split up, okay? So we're going to bring that right down as is. Here we have, you're right, an acid starts with an H. So what's the rule for acids? It's all about if they're strong or weak, right? Acids, strong or weak. How can you tell if they're strong or weak? Take a look at the table. So HNO3. Oh, look at that. HNO3. Okay? HNO3 is one of those six. It's a strong acid. And what's the rule with strong acids? They like to split apart into their ions. So when they split apart into their ions, we're going to have H plus, and we're going to have NO3 negative, negative, negative. Oh, goodness gracious, when I try to erase, this is what happens. And so we're going to, I'm going to leave out my AQs right now just for speediness, but you guys know what I'm talking about. Okay, so we get our ions here. And I'm just going to split them up so that I can move them around. So it broke up into its two ions. And then we've got water, which is a molecule. You got to love water. It's a molecule. So we can just clone it and bring it right back down. So once again, we have our entities present. If you recall, our next step is identifying as acid or base. So we use our table to find out where they are. So NH3, we're searching, NH3, use the chemical formulas or use the names. Ammonia, NH3, NH3. Do you see it there? Do you see it there? NH3. Oh, I see it. It's right there. It's on a base side, okay? Check both sides, but I think you're going to find it just on the base side. So that is a B. We look for our H3. And here's another one, guys. You might search for this forever. And what I want you guys to realize is this particular table likes to use the NH3 positive. So you can put down H plus, but you've got to recognize that you need to search for H3O positive. Okay, that's what you need to search for when you're looking at that. So be aware of it. It's the same thing, but on our table, you will not find H plus. You'll find H3O positive. And we find it very quickly on our table. And H3O positive, can you find it? Boom, 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 boom. Right here, H3O positive. So it's pretty high, okay? But it is definitely an acid. So that gets an A. What happens? Okay. That gets an A. And our NO3, again, you search and search and search. All right, and you find out what it is. And then this one, you'll find out again. I'm going to put my A up here. And you clone that because you'll find this is an A. And you'll get used to it because water's always an acid and always a base. All right, so, oh, goodness gracious. Always a base. Excellent. Okay. And this guy here, you'll find he is a base. Okay. So he's going to be a base. Now, just because we're running out of time, I want to finish this question up quickly. I already have it finished, so I'm going to go to that. But we've done steps 1 and 2. Now we have to do steps 3. And steps 3 are when you find your strong acid and your strong base. Remember, strong acid, top of the table, strong base, bottom of the table. So there's our entities and our acids and bases and our strong acid and our strong base. This works out to be the highest on the table, so it's our strong base, a strong acid rather. And this works out to be our strong base, okay? And when we remember our definitions, the acid donates, right? It donates an H. So this guy's going to lose an H. He's positive to begin with. He loses an H, so he becomes more negative. He becomes neutral. And this guy gains the H, so he becomes positive. And this is the reaction we have. And a lot of people are like, well, what's that have to do with ammonium nitrate fertilizer? Remember, nitrate's in the beaker. It just doesn't happen to be in this reaction. But nitrate's there, so once we make some ammonium, it will mix with the nitrate to make our product. So our product's going to get made, but it's kind of a second reaction. It's a reaction happening behind the scenes. So this acid-base reaction makes the ammonium, and then that ammonium reacts with nitrate that's in the beaker to make your ammonium nitrate. So that's where the compound comes from. One last thing, we've got to figure out if this is greater than or less than 50%. So get your hands. This is going to be your left hand. This is going to be your right hand. Which one is higher? Okay, check it out. So H3O and NH4. So H3O is right there. NH4 is right. Let's find NH4. That's NH3. So NH4 is our acid, sorry. And our base is H3O positive. Sorry. Oh, gosh. NH4 is our base and H3O is our acid. So we have our acid here. H3O is our acid. And we have our base is NH3. And I found my NH3 there earlier. See it there again, guys. Oh, yep. So there's NH3. Okay, so our right hand is down here, NH3, and our left hand is right up here. Okay, so our left hand is high enough again. And so if you remember the rule, our left hand is high, our right hand is low. Throw that out because we've got greater than 50%. We've got greater than 50%. So hopefully that helps. We got a chance to do 2 of these. There's 8 or 9 of them to work on your assignment. I guess I didn't finish it. And so it's going to be greater than 50%. It's actually a lot greater than 50% because if you notice in the question, they told me it was a quantitative reaction. So I know it's greater than 50%, but because they told me it was a quantitative reaction up here, I can assume it's 99%. But it's always nice to double check that as well. Okay? So sorry so long, but I think it's good to go over those examples, and we can talk about a few more on Tuesday or Thursday if you need it. Thanks so much. Take care.